Good morning. I'd like to welcome all of you here, and I'd like to welcome all our students who are taking the course online. This is our second lecture in Calculus 2. Last night when I was browsing the homework forum, I noticed, by looking at your introductions, that many of you took Calculus 1 with me earlier this year. So it's a particular joy to read so many familiar names. I'm glad that you joined us, and I hope that you will share your success story with other students in this class who are taking calculus for the first time, delivered online. Actually, some students are taking an online class for the first time in their lives. It's going to be an engaging experience. One of the most important aspects of this class is an active forum, where students help one another when they get stuck. Also, on the forum you can actually check your final answers to homework problems and offer hints to others. And of course you can share your frustrations, because there will be some challenging homework problems. If you're joining us for the first time, be sure to introduce yourself on the homework forum and look at the homework policy, look at the course policy, and if you have any questions, just ask on the forum. As you recall, Calculus 1 ended with the celebration of the fundamental theorem of calculus. There were two parts. One was the differentiation part, and the other part was, what was it? It was the evaluation part, yes. So we concluded the semester with simple applications of the fundamental theorem. In today's lecture, we will illustrate one application of the evaluation part of the fundamental theorem of calculus. Let us recall how to calculate the area under the graph of, say, a parabola, say y is equal to x squared, between two vertical lines. So say I have the parabola x squared, and I'd like to evaluate the area bounded by two vertical lines. Say the first line will be x is equal to 1, and the second line will be x is equal to 2. So I am talking about this area here. How should we do that? How should we solve this example? Well, we need to set up the definite integral. The definite integral will be the area that I just shaded here. And then we will use the fundamental theorem and antiderivatives to calculate that area, and we obtain an exact number. We don't need to write the limit of the Riemann sum anymore. So this area, A, is equal to the integral from 1 to 2. You can write x is equal to 1 to x is equal to 2, if you will, of the function x squared. And don't forget to write this dx. Dx is the part of the integral symbol. So the fundamental theorem of calculus tells us that if we know an antiderivative of x squared, we can calculate this integral by simply subtracting the antiderivative evaluated at 2 minus the antiderivative evaluated at 1. So remember that the general antiderivative of x squared is 1/3 x cubed plus a constant. So if I let f of x to be, say, 1/3 x cubed, and I pick the constant to be 0, then this integral is equal to f of 2 minus f of 1, which is 1/3 times 2 cubed minus 1/3 times 1 cubed. So this is equal to 8/3 minus 1/3, so 7/3. A little bit more than 2. I always have been amazed by the fact that when we are calculating the areas bounded by some curves, that we can actually get fractional numbers or even integers sometimes. Because the first formula for the area bounded by some curves that I knew as a child was the area bounded by a circle. And that area was pi times r squared. And pi is an irrational number. An irrational number means that that number cannot be expressed as a fraction of integers. But this one can. And this one is 7 divided by 3. So to this day I find this amazing. So now notice that this area can be considered as the area bounded by two curves. One is y is equal to x squared, and the other one is y is equal to 0. So in general, now let's talk about the situation where we will have an area, a region bounded by two curves, and the bottom one is not necessarily just the coordinate axis. Let us start with the following general situation. We have two curves and two vertical lines. And we will then have a region that will be bounded by these lines and the curves. And the goal is to come up with a general formula for the area of this region. So say we have these two curves. This blue curve, y is equal to f of x, and another curve, y is equal to g of x. Now, we also have these two vertical lines. X is equal to a, and another line, x is equal to b. So we're interested in this region. In today's lecture, when we talk about regions bounded by curves, we always will consider the area of that region as a positive number. So remember in Calculus 1, when we try to calculate the area under the graph of some function above the x-axis, we subdivided that region into a bunch of thin rectangles. And then we wrote the formula for one rectangle, and then we added up the areas of all these rectangles and we obtained an approximation of that area. That summation was called the Riemann sum. We can actually follow the same process here to derive a formula for the area bounded by these two curves. So let's consider thin rectangle like this and say that it's located around x star, and the width of that rectangle, this width here, will be delta x. Now, what is the height of that rectangle? How would we get the height of such a rectangle? Well, let's see. What's the what are the coordinates of this point here? This point lies on the graph of f, so the coordinates are x star, comma, f of x star. And the coordinates of this point, x star, g of x star. Okay, so we have 2 points, so now we can apply the distance formula to get the height of that rectangle. You could use the square root of the difference of 2 coordinates, but notice that since the first coordinate is the same, the distance between these 2 points is simply the absolute value between g and f. So let's write down the area of this one blue rectangle. That would be the height, so the absolute value of f of x star minus g of x star. So this is some function h of x star, the height at x star. And if we would like to get the area, we need to multiply that by the width of the rectangle. So this is the area of one rectangle. But now to approximate the whole area of this region, we need to add these areas of these rectangles together. So the approximate formula for the area will be the summation of h of x star, and here I need an index, times dx, where I varies from 1 to some number n, where n is the number of these rectangles that approximate our region. So let me sketch another one here, and another one here, etc. So that would be the approximation. But remember, in Calculus 1, what we did in order to get a better and better approximation, we let n to be larger and larger. So formally, we pass to the limit in this summation. So then the area of the region bounded by the curves f and g is then the limit as n goes to infinity of the summation of h of xi star delta x. I goes from 1 here to n. Have you seen a summation like that before? So naturally, this is the definition of the integral of h between a and b. So that the summation is the integral from a to b of h of x dx. So in other words, And now remember that the height was the absolute value of the difference f minus g. So now we have the final formula, which says that the area of the region bounded by the two curves f and g between two vertical lines x is equal to a and x is equal to b is the integral of the absolute value of f of x minus g of x dx. And that's the only formula in our introductory lecture that you need to memorize. Let's look at some examples. So in our first example, let's look at the area bounded by the parabola y is equal to x squared and the line y is equal to x. So here is our parabola, x squared, and the second function is y is equal to x. So just the function g of x is equal to x. And the goal is to calculate this area. So we will need to apply this formula. How would we do this? Well, the limits of integration are from 0 to 1. So our area, A, is equal to the integral from 0 to 1 of the absolute value of x squared minus x dx. And now, how do we solve an integral when we have the absolute value? Well, we have to see if the quantity inside the absolute value is always positive on the interval on which we are considering our function. In this case, actually, if you look at this graph, x squared is less than x. So this quantity is negative between 0 and 1. So our absolute value will be equal to actually negative x squared minus x dx, or just x minus x squared dx. Okay, so now we apply the fundamental theorem, right? We look for an antiderivative of this function, and then take the difference of these two antiderivatives, of that antiderivative at 1 and at 0. So what's the general antiderivative of x? It's 1/2 x squared plus a constant, but here we don't need to write a constant because we just look for any antiderivative, minus 1/3 x cubed. Remember, I'm using this formula that the integral of x to the n dx is equal to 1 over n plus 1 times x to the n plus 1. That's calculus 1, right? A table of antiderivatives. So now, remember that we denoted in calculus 1 this antiderivative as the capital function f of x. So we evaluate that at 1 and at 0, and then we get 1/2 1 squared minus 1/3 1 cubed. So that is f of 1 minus now f of 0. So 1/2 0 squared minus 1/3 0 cubed. This is 0. That's 1/2 minus 1/3. So our final answer is 1/6. And that's reasonable, right? This shaded area here is kind of small, right? This is the unit square, so this area should be definitely less than 1. So probably our answer is correct. Do you have any questions? Yes? Oh, Monica is asking, do we have to use the absolute value formula? Do we have to use this formula for an example like this? So if you don't use it, what would you do? Let me repeat. So Monica is saying that this area is just the difference of the area under the line y is equal to x and the area under the parabola x squared, right? So I could calculate the area under the black function g of x and then subtract the area of the region bounded under the function x squared. Let's do that. So let's see if Monica is correct. So we would like to get this black area. So first let me get the area of the right triangle. So the area under the graph of the function g of x. I think I called the function x as g of x. And this one, the blue one, was f of x. Okay, so the area of this triangle, so it was 0, 1, 1. How would we calculate this? That's the integral from 0 to 1 of x dx, right? So this is, what is that? 1/2 x squared evaluated at 1 minus 1/2 x squared evaluated at 0. So that is 1/2. Now we evaluate the area under the parabola x squared. So this area, so that's the integral from 0 to 1 of x squared dx. So that is 1/3 x cubed evaluated at 1 minus 1/3 x cubed evaluated at 0. So you can check that you get 1/6. Sorry, you get 1/3. Okay, so the area of that thin black piece then will be the difference of these two areas. So then our area of this thin piece will be 1/2 minus 1/3, which is 1/6. So we got the same number. And Monica is correct. In the very special case when the functions do not the graphs do not intersect each other inside the interval, if one is always above the other, and say if they're in the first quadrant, you simply can subtract the two areas, the area under the graph of one minus the area under the graph of the second one. But notice that what we did here is we obtained the integral from 0 to 1 of x dx and the integral of 0 to 1 of x squared dx. And then we took the difference. So essentially, remember that there's this property of integrals that if you have two integrals over the same interval, That's the one integral over that interval, so from 0 to 1, of x minus x squared dx. And this is the integral that we got right here. So Monica's idea is good, but only it applies to the case where you have a simple situation. In general, when two functions intersect each other many times, the generalized formula, which is this one, will work. So let's look at another example, this time a little bit more challenging. Let's now look at another example in which the curves will intersect themselves inside the interval on which we are considering our region. Say, let's consider this. Cosine of x and sine of x are these two curves, sine of x and then cosine of x. And then we would like to get the area of the region bounded by two vertical lines, x is equal to 0 and x is equal to 3 pi divided by 4. So that's the first vertical line, x is equal to 0. And that's the second one, x is equal to 3 pi divided by 4. So the area trapped, the region trapped between these two curves and the lines is this shaded area and this shaded area. Do you want to get started on your own? You have a formula, and then in a minute or two, we will solve this problem together. If you are interacting with us online, it's a good time to pause this video. Try to solve this problem on your own first. Don't worry if you get stuck, because I will help you understand how to do this problem in a minute. Okay, so we just need to set up the integral, right? So the area A is equal to the integral from 0 to 3 pi divided by 4 of the absolute value of cosine of x minus sine of x dx. So how do we solve an integral of the absolute value? Well, we have to, in order to get rid of the absolute value, we need to know the sign of what's inside. So let's look at the graph here. In the very beginning, between 0 and that intersection point, cosine was above sine, right? So probably we will split that integral into two integrals. The first one on the subinterval 0 and that number here. Let me call that little x. And then from little x to 3 pi over 4. So we need to find that little x. How do we do that? How do we do that? Well, these two curves intersect each other, right? So both the horizontal and vertical coordinates are the same here. But if that's little x, the vertical coordinate is cosine of x, and at the same time it's sine of x, right? So in other words, sine of x must be equal to cosine of x at that intersection number. So what is the value of x when that happens? When is cosine equal to sine? Pi divided by 4. And many other numbers, right? But in our picture, it's only pi divided by 4. How can we find out that this is the case? Well, remember, in pre-calculus, or even in Calculus 1, I reviewed the trigonometric functions, and if that's angle t, then the coordinates of this point are cosine t, comma sine t. So cosine t is equal to sine of t when t is equal to pi divided by 4. And when t is equal to pi and pi divided by 4, and so forth. But we're only interested in the domain between 0 and 3 pi divided by 4, so the only solution here is these two coordinates are the same when t is pi divided by 4. Alternatively, what you could do is say this. Well, cosine is positive in between 0 and pi divided by 2, so I can divide both sides by cosine. And then I get sine of x over cosine of x is equal to 1. Or tangent of x is equal to 1. So x is equal to tangent inverse. What's inverse tangent of x? Sorry, of 1? Pi divided by 4. So now we will split that integral into two integrals. The integral from 0 to pi divided by 4. And the integral from pi divided by 4 and 3 pi divided by 4. Okay, so what's next? Well, the reason why we split that integral into two integrals so that the quantity inside the absolute value doesn't change the sign. So we know the sign of that quantity. What is it? So cosine is bigger than sine on that interval, right? So I'm using color green to indicate that cosine is bigger than sine. So simply I can just drop the absolute value. And what should I do in the second integral? From pi divided by 4 to 3 pi divided by 4. On that interval, notice that sine is bigger than cosine. So this quantity will be equal to negative cosine of x minus sine of x, which is sine of x minus cosine of x dx. Okay, so the rest is applying the fundamental theorem of calculus. You find the antiderivative of this integrand, and then you evaluate this integral, and then you do the same thing for this integral. So I'll leave that part to you to finish, and to make sure that you do this problem correctly, please start a thread on the forum and check with others if you got the right answer. You could tag your online discussion by saying that this is lecture 2 and the example with sine and cosine. So maybe like lecture 2 example 3 or lecture 2 cosine. so that others will know that you're referring to this example. In this example, we will consider the region that is bounded by the horizontal line y is equal to 0, the line y is equal to x minus 6, and the curve y is equal to square root of x. So notice that unlike in the previous example here, this region is not directly seen as the one trapped between the graphs of two functions and two vertical lines, right? So what can we do here? Split it, yes. How would you split it? 6. What is 6? Oh, from x is equal to 0 to x is equal to 6. Consider that as one problem. And then from x is equal to 6 to x is equal to 9 as the second problem. By the way, how did you know that this was 6 here? Well, look, yes, you look at the equation y is equal to x minus 6. So y is equal to 0 when x is 6. Okay, so let's set up the integral this way. Actually, the two integrals that correspond to these two regions. How about I'll call that region 1 and this region 2. So then the area of the region 1 is equal to, well, we apply our formula, and we already see that the function square root of x is above the horizontal line. So if I write the square root of x first, then actually I don't need the absolute value because the square root of x is bigger than 0, right? So this is simply just the integral from 0 to 6 of the square root of x dx. And the area of the second region is the integral from 6 to 9. And the upper function here is the square root of x, and the lower is x minus 6, right? Don't forget parentheses here. So I'm just applying our formula that we talked about earlier in the lecture. So this can be simplified since, as you can see in this picture, the square root of x is bigger than x minus 6, between 6 and 9. So I can skip the absolute value, and then I get just the square root of x minus 6 minus negative 6, so it's plus minus x plus 6 dx. So then we need to solve this integral, calculate this integral, and add the two areas. So the area that we are interested in, this area, is equal to A1 plus A2. Should we calculate these integrals very quickly? Why don't you do that, and we'll just check in a second. So let's see if what you got is what I prepared here on this whiteboard. Okay, let's start with the first region, A1. So we are evaluating the integral from 0 to 6 of the square root of x, right? So the general antiderivative of the square root of x is x to the power 3/2 times 2/3 plus a constant. So that's an antiderivative, and I evaluate that between 0 and at 6 and then at 0. How did I get that formula? Well, that's calculus 1, right? Remember, the integral of x to the n dx is equal to 1 over n plus 1, 1 over n plus 1 times x to the n plus 1 plus some constant c. So here, n is equal to 1/2. It's x to the power half. So I apply this formula, and then I get this. Now evaluating this expression at 6, so I have 2/3, 6 to the power 3/2. At 0, this is 0, so I didn't even write that down here. And then I would like to get a nicer expression here, so I'm splitting 6 to the 3/2 as 6 times 6 to the power 1/2. That is 6 to the power 1 times 6 to the power 1/2, right? So then I can simplify this fraction here, and then the result is 4 square root of 6. Is that what you got? So that number represents this area here. And then I calculated the second area. Actually, that calculation was more involved. The integral from 6 to 9, so it's the integral from 6 to 9 of the difference between the square root of x and the line y is equal to x minus 6. Square root of x is bigger than x minus 6 there. See the picture? So I can skip the absolute value here. And then I get the integral from 6 to 9, the square root of x minus x plus 6 dx. Here is an antiderivative of this expression. We did it term by term. And then I evaluate that antiderivative between at 9 and subtract from it this antiderivative at 6. So at 9 I get this expression, 2/3 9 to the power 3/2 minus 1/2 9 squared plus 6 times 9. And then at 6 I get this expression, 2/3 6 to the power 3/2 minus 1/2 6 squared plus 6 times 6, right? 6 times 6. Don't forget to write this expression in parentheses, otherwise you may get an error. So after simplification, I skipped a couple steps here. I just wrote down the final answer, which is 27 divided by 2 minus 6 square root of 6. And finally, I'm adding up the two areas. So area 1 was 4 square root of 6, and then the other one was 27 divided by 2 minus 4 square root of 6. So actually, notice that this and that 4 square root of 6 cancels. So the final answer is surprisingly nice, 27 divided by 2. So what do you think about that example? It was actually quite involved. We had to split our region into two parts, and then each integral was not super complicated. Well, not very hard to do, it's just tedious, a lot of calculation. And the number we got surprisingly nice. So maybe there is another way how we can approach that problem and simplify our calculations. If you are watching this video on a tablet, what you could do is take this picture and rotate it by 90 degrees so that the x-axis becomes vertical. Tell me why, you see. You see the same region, but this time the region is bounded by two functions, not three, right? So I'm not going to rotate the entire wall, but I'm going to rotate my head. And now this line lives above this curve. So if I were to integrate from this point here all the way to this number, which is, by the way, if that's 9, right? So the square root of x is 3. So if I'm going to integrate from 0 to 3 in this direction, all I see is that there's one function here and another function here. Well, what might be a little bit confusing is to write this down, because we have to interchange the role of x and y. I'd like to give you a minute to try to set it up, and then we will do it together. I sketched a miniature of the rotated picture right here. So now y is a horizontal axis, but it goes to the left, and then x is the vertical axis. Okay, so did you try to set up the integral? Remember, now we will try to integrate in this direction, going up, or in this new picture, going to the left. Why are we doing this? Well, as you saw, the first approach, by dividing the region into two regions, was doable, but it was quite involved. There was a lot of work. Two parts, and the second integral was a little bit of work. By interchanging the role of x and y, we can simplify this problem. But before we do that, we need to represent the same curves, or the line and the other curve, as functions of y, because we will be integrating with respect to y. So if y is equal to x minus 6, then x is equal to, what's that function of y? Y plus 6. And if y is equal to the square root of x, then x is equal to what function of y? Y squared, yes. So then our area will be calculated as the integral. Let's first make sure that we get the limits correct. So we are starting at 0, and we're going all the way to this point here. So y changes from 0 to 3. Why did I know that was 3? Because the coordinates at this point are 9 and 3. And then we need to write the integrand is the difference of two functions of y, which are, well, one of them is y plus 6, and the other one is y squared. So let's calculate this integral. Notice that y plus 6 in this picture is above y squared. Or if you're looking at the original picture, y plus 6 is to the right of y squared, right? So I don't need that absolute value, actually, because this quantity is positive. So let's find the antiderivative of our expression. So we will apply the Fundamental theorem of calculus, of course. The evaluation part. So the antiderivative of y is 1/2 y squared. What's the antiderivative of 6? 0? Is that 0? It's a constant. The derivative of 6 is 0, but the antiderivative of 6 is 6y. And the antiderivative of y squared is 1/3 y cubed. And we need to evaluate this antiderivative at 3 and then subtract from this the antiderivative at 0. Some of you are puzzled. What's the question? How did I get that 1/3 y cubed? Well, that's calculus 1. So some of you who took calculus 1 a while ago, you have to really get current. This is the material from the lecture of antiderivatives. I got this from y squared by applying the formula, the general formula that the integral of x to the n dx is equal to 1 over n plus 1 x to the n plus 1 plus c. Okay, so let's evaluate this. At 3, I got 1/2 3 squared minus, sorry, it's actually plus 6y here. So plus 6 times 3 minus 1/3 times 3 to the 3rd power. And let's evaluate this expression at 0. So it's 1/2 0 squared plus 6 times 0 minus 1/3 times 0 cubed. So that's actually 0. So what do we get? 9/2 plus 18 minus 27 divided by 3, 9, right? So this is 9 plus 9/2. 9/2 is 4.5. Or let's just convert everything as a fraction, right? So this was 9. So it's like 18 halves, right? So 9/2 and 18 halves is 27 halves. Wait a minute. I saw that number before. Where is it? It's got to be the same, of course, yes. So look, I got the same answer. Well, this calculation, it's much easier than the previous one. I'm very glad I got the same answer. Most of the time, as you know, when you try to calculate, there's somewhere that I make a mistake. I remember I almost forgot that put the wrong sign here. But I'm glad that finally we got that right. Well, this lesson wasn't that involved. As you probably realize, the lecture is only the beginning of your journey to master the material. You try to interact with the video, and after you did the basic examples, then you start doing homework problems, and you read the notes if there's new material in the notes. Always try to do homeworks by yourselves first, before you ask for help on the forum. But our forum is really amazing. We help one another. And actually what I'd like to do now is to finish this lecture and check the forum, what's going on. I'll see you there shortly.